Special Relativity Theory. Part 4-2. Introducing a new approach to the derivation of Lorentz transformation. Lorentz transformation. As I mentioned in previous sections, the Lorentz transformation is the core of Einstein's special theory of relativity. It is supposed to translate the quantities of time and space between two inertial systems. I have already presented some obvious contradictions to this theory. We would continue our investigation by introducing a new and more understandable approach to deriving of the Lorentz transformation. Lorentz transformation. Introducing a new simple approach of derivation. Assuming that the values can be translated between two inertial systems using the following linear equations, the problem would be limited to finding the parameters a, b, c, and d in equations 1 and 2. Equation 1. X prime equals ax plus bt. Equation 2. T prime equals ct plus dx. Substituting x prime equals 0 in equation 1, we get x equals minus b over at. Substituting x equals 0 in equation 1, x prime equals bt. Substituting x equals 0 in equation 2, t prime equals ct. Combining these results, we obtain equation 6, x prime equals b over ct prime. Considering the relative velocity v, x equals vt, x prime equals minus vt prime. For equations 3 and 6, minus b over a equals minus b over c equals v results in c equals a, b equals minus av, and we get equation 7, x prime equals ax minus avt. Equation 8, t prime equals at plus dx. For x prime equals 1 and t equals 0, 1 equals ax, so we get the viewed length of the rod from k, x equals 1 over a. For x equals 1 and t prime equals 0, 0 equals at plus d, or d equals minus at and x prime equals a minus avt. So we obtain the viewed length of 1 meter rod in k from k prime. X prime equals a plus vd. According to relativity, x equals x prime, then 1 over a equals a plus vd. Or d equals open parenthesis 1 over a minus a close parenthesis over v, so we obtain general equations 9 and 10. So we get easily the equations 9 and 10, applying the equality of the velocities of k and k prime relative to one another, an equal viewed length of two 1 meter rods, one in k and the other one in k prime. Equation 9. X prime equals ax minus avt. Equation 10. T prime equals at plus open parentheses 1 over a minus a close parentheses times x over v. These equations satisfy the relativity conditions for any given a. For a equals 1 we get Galileo transformation. Equation 11. X prime equals x minus vt. Equation 12. T prime equals t. If we apply the postulate of the constancy of light speed, i.e. x equals ct, and x prime equals ct prime, we get the Lorentz transformation, as shown on the right side of this page. The general form of the transformation equations. The equations 9 and 10 are the general form of equations for translating time and position between two inertial systems moving with velocity v relative to one another. It is obtained, as shown, only by applying the relativity principles. These equations satisfy the relativity conditions for any given A. A should be determined for any specific physical condition. Length contraction and time dilation are not the consequences of constancy of the light velocity, but these result from relativity principles contained in the equations 9 and 10. As we saw, Lorentz transformation is obtained by putting x equals ct and x prime equals ct prime in equations 9 and 10 and getting A equals 1 over the square root of 1 minus v squared over c squared, or A equals gamma. To be continued.